Before the coffee, we have 2 talks, 2 hours, with a half hour for discussion. So nominally these are 45-minute talks. And our first speaker is Greg Hammett from Princeton, and the title of his talk is Measurements and Gyrokinetic Simulations of Electron Transport in NSTX.
Thank you. I want to first acknowledge that a lot of the slides I'll be showing are from Luke Peterson or Howard Yu. Luke is a graduate student working with me, and Howard is on the research staff. Actually, he's with Nova Electronics. There are a lot of people involved in experiments, and this is a list of all the collaborators on NSTX and their institutions. And then the usual support from DOE and other sources. So let me start. I was asked yesterday to provide a little more tutorial background, try to explain more of the fusion jargon. So please stop me as we go along. It'll be more productive, particularly early on, if you stop me at the beginning to define terms or something. So as Steve talked about yesterday, our big motivation is not only to understand confinement, but to improve it. Can we find configurations that can improve confinement? NSTX is the National Spherical Torus Experiment at Princeton. It's a high-performance spherical torus that has achieved very high beta. The central pressures are of order the magnetic field pressure have been achieved in this device. Spherical torus is something of an oxymoron. It's still topologically a torus, but it's been squashed together, so it's overall kind of a sphere, but it has a hole down the center. There's a current driven down the center to provide the mean toroidal field that goes around. These devices, because of their unusual configuration, their high aspect ratio, the high ratio of minor radius to major radius, it's part of what has allowed them to achieve these very high betas. And ion transport is typically neoclassical in H modes in these devices, in part because of strong sheared flows. This device is about almost a meter major radius, carries a current of 1 megamp, and they're in the process of working towards upgrades to 2 megamps. Okay. So although the ions have very good confinement, just collisional confinement can explain them often, the electrons are still quite anomalous, and we need to understand what it is that drives the electron transport. And STs need to improve. In order to make a good ST fusion reactor, we need to find ways to improve core electron confinement. And NSTX is, we believe, well equipped to study electron confinement. This shows the electron temperature versus major radius from about the center of the machine out towards the edge. When they had 4 megawatts of external neutral beams heating the plasma, or 6 megawatts. And you see the central temperature, in fact, did not go up at all. So there was something that seemed to be pinning the temperature and not allowing it to rise any further. However, under certain circumstances, they're able to tailor how the plasma is made and achieve what's called an internal transport barrier, an ITB. There are also edge transport barriers that were discovered first, so that's why these are called internal transport barriers. And these lead to dramatic improvements in core confinement. You can see the electron temperature more than triples, and we get this region where where we can have an extremely steep temperature gradient. And this is a region where the background turbulence that was keeping this temperature flat, where this background turbulence was suppressed. So I'll basically be trying to discuss these types of observations and phenomena and try to understand what goes on in them. Yes, this one has actually less power than these other two. Yeah. So this has less power, but the Q profile was different. And that was the trick that allowed it to have better performance. Yes, although I'll have some shots that are RF only. So I'm going to start off with a mini tutorial on the bad curvature drive of tokamak instabilities. I don't want to some of you are from outside of fusion research, and so if you do MHD turbulence all the time with stirring in a box, you don't even think about you don't need to think about some of the mechanisms that drive the instabilities, but I'll talk a little bit about that. And that feeds into why negative magnetic shear is good. I'll briefly discuss Yanko and Dorland's surprising prediction that there can be significant transport driven by electron temperature gradient drive of turbulence. We call this ETG turbulence. I'll talk about some of the measurements that have been recently made confirming the existence of these small-scale electron gyroscale fluctuations on NSTX and observations of internal transport barriers with negative magnetic shear. These two together are both consistent with expectations from these ETG theories. I'll talk about some of the work that Luke Peterson has been doing with me, doing some initial nonlinear simulations with the gyro 5-dimensional gyrokinetic code. And we're working towards eventually doing detailed comparisons with microwave scattering measurements. And I do want to emphasize that I'm going to be focusing in this talk on ETG. But even we will point out that ETG doesn't explain everything. It looks like trapped electron modes are also playing a role in some of the discharges we're looking at. And other people at Princeton and elsewhere are looking at other possible causes of electron transport on NSTX. In some cases, there might be microtearing going on. And there's also some correlations of reduced confinement with GAE modes. These are high-frequency global alphane eigenmodes. I'm going to focus on the ETG stuff here. I'll skip that till later. Okay, so we're going to start off with an intuitive picture of gyrokinetic turbulence and how to reduce it. Okay, so freshman physics, you all know how a pendulum, stable pendulum works. Its oscillation frequency is the square root of G over L, and the fonts got messed up in going from my old PC to this Mac, so that should be n omega there. So the frequency of a pendulum is square root of G over L, where G is the acceleration due to gravity, L is the length, as the founder of physics in this institution would have well known. Now, if you try to balance a pendulum upside down, if this was a rigid rod and you try to balance it upside down, we all know it's going to be unstable, it's going to fall over, and the growth rate is going to be square root of G over L again. You can think of G or L as negative compared to this, and so the frequency, take a square root, you get an I there, and so you get a growth rate. Now, I introduced these two just to remind you and how they're related to density stratified fluids. If we have a fluid with a density gradient, where the density is more dense on the bottom, and the density, say if there's a salinity variation, is less dense on top, if that density variation goes like e to the minus y over L, where y is the vertical height, you get stable oscillations in the right range of wave numbers in this type of fluid, whose frequency is square root of G over L again. It's just that L, instead of being the length of the pendulum, is the scale length over which density is varying here. Now, if you have an higher density on top, lower density on bottom, that is the classic Rayleigh-Taylor instability, and the growth rate is square root of G over L again. Now, in fusion plasmas, we're dealing with magnetically confined plasmas, and so and we're looking at toroidal plasmas. So we dominantly have a toroidal field that goes around like this, that confines the particles. And there's an analogy between the bad curvature, or between the inverted pendulum or the Rayleigh-Taylor instabilities that we just talked about, and what's called a bad curvature instability in fusion plasmas. So we have particles trapped on this magnetic field. They gyrate around the magnetic field. They can follow the field lines. So these particles are rapidly going around this circle. And you can think of the plasma as being a heavy fluid. It has mass and inertia that's being confined away from the walls by a magnetic field, which you can think of as a light fluid. It exerts the pressure, but no inertia, no significant inertia itself. And so we have this plasma here that is experiencing a centrifugal force outward. The particles are going around a circle. They have a centrifugal force outward. The effective G, that got messed up, is v squared over r, where v is the velocity of the particles. And we have this situation, the effective gravity is down. We have a heavy fluid on top of a light fluid. That's Rayleigh-Taylor unstable. And so we get a growth rate that's square root of G effective over L. G effective is this v squared over r. If I plug in a typical thermal velocity of ions, This is V thermal over the square root of RL, where R is the radius of curvature of the magnetic field. And this is the typical interchange growth rate of a lot of different types of MHD and drift microinstabilities. So this is the main mechanism that drives a lot of instabilities in fusion devices. Here, L is the, instead of being, it's the gradient scale length of the pressure in MHD. In drift waves or microinstabilities, it's some kind of combination of grad N and grad T here, depending on what parameter regime you're in. There's a little analogy you can think of. Now, if this was always the case, we would have given up on fusion long ago. Ed Teller said this is like trying to confine Jell-O with rubber bands. And the trick is to, as we all know, is to introduce a twist to the magnetic field. So we do not have a pure toroidal magnetic field that just goes around in circles. We also have a poloidal field that causes the field lines that are initially out here to twist around to this side. And if you go through these same arguments, if we follow a field line out here, looking down on top of the machine, follow a field line there, and because of the poloidal field that causes it to twist around here, this side of the tokamak is the good curvature side. It's stable. Here we have a light fluid on top of a heavy fluid, and so that's the stable side. And so it's that twist that's crucial for fusion devices, toroidal fusion devices to work. And you can think of it like a honey dipper, that if you just pull out the honey, it's going to pull out the honey dipper, honey's going to drip off. But if you twist it at just the right rate, you're continually carrying honey from the bottom unstable side, where gravity's pulling you away from the center, to the top, where gravity's pulling you back towards the center. And you get confinement when you twist it at the right rate. Any questions about that little toy picture? Now, these mechanisms that I've talked about can be seen in gyrokinetic simulations in a tokamak. This is a cutaway view, like the movie Steve Cowley showed yesterday. We see the turbulent eddies are largest amplitude on the outside of the machine. This is the bad curvature side. This is the stable side. So the turbulence is damped over here. We see that we essentially, there are eddies here. These are kind of interchange modes, really Taylor fingers, if you want, that are pointed outward. That's the direction of the effective gravity. As the particles are going around, they're feeling an effective gravity that's outward here. So that's why these fingers try to elongate radially, but because of nonlinear dynamics, they've been broken up. You can also see that these structures are very extended along magnetic field lines, and those field lines have a twist due to the poloidal field. So we have short wavelengths perpendicular to the field. Particles move very quickly along the field line and make things fairly isotropic, or much more isotropic along a field line than perpendicular to the field line. A key effect that is crucial in the nonlinear dynamics of these modes are zonal flows. These are flows that stay within a zone, within a radial zone. So they go around like that, and they have shear as you move radially. And it's that shear that breaks apart the radial fingers and provides saturation. Now this is it's a toy model, but there's some interesting, there's some closer analogies than you might think. As Einstein taught us, accelerating frames of reference, and you cannot distinguish being in an elevator accelerating versus gravity. And so there really is an effective gravity as particles is being accelerated around a circle. So there is a quite close analogy. If you balance this, kind of a local growth rate in the bad curvature region, if you balance that local growth rate with a kind of alphane rate to the good curvature side. So if we try to have an interchange mode over here, but it's going to bend the field line and propagate along the field line to the good curvature side. So if we say that the local growth rate over here has to be faster than the rate at which an alphane wave can connect us to the good curvature side, and that alphane rate is just VA over L parallel. L parallel is the connection length 2 pi QR. 2 pi R is once around, and Q measures the twist. So it tells you how far you have to go before you twist around. Q is the rate of twist, and so that tells you how far you have to go before you get around to the inside. If you balance these two, then you find at marginal stability that you get that ratio of that term gives rise to the MHD ballooning parameter, alpha, this RQ squared d beta dr that comes out in S alpha models of ballooning. And this brings us to part of why STs are of interest. This toy model doesn't completely explain why STs are as good as they are, but it kind of gives you the picture. The magnetic fields in a standard tokamak with a large aspect ratio look more like this. Magnetic field lines have kind of so there's a certain length to go around until you get to the inside. In an ST, because of the large aspect ratio, the toroidal field is extremely strong here, while it's relatively weak here. So there's a rod going down the center producing the toroidal field. So that makes field lines wrap around multiple times here and very quickly relatively quickly go through the bad curvature region. And this helps reduce the instability drive. This, in combination with other effects in STs, is what gives them their good confinement. Any other questions? Now, you can also look at these things in terms of the drifts of individual particles and E cross B charges that charge up. I just thought of this last night. So this is a classic from Longmire and Rosenbluth paper, Rosenbluth and Longmire paper. But if this is a zoom in on the outside region of a tokamak and looking at the stability of perturbations between a hot and a cold region of plasma. But even if you're MHD stable, so you're below that threshold for driving MHD modes, you can still drive drift waves or micro instabilities, basically driven by the same perpendicular dynamics but with different parallel dynamics. These drift waves occur at small scales by including FLR effects like electron pressure gradient term in Ohm's law. These allow the plasma to slip through the magnetic field, so you no longer have the stabilizing influence of bending the magnetic field lines. So if you tried, and these FLR effects give rise to a growth rate with the same V thermal over the square root of RL scaling, but with now an FLR factor that requires you to have a finite size perturbations relative to the gyro radius to get a significant growth rate. Now, if you balance this with Landau damping or phase mixing from the vertical drifts, basically say that this local growth rate has to be faster than some multiple of ky V drift. So V drift are the grad being curvature drifts down vertically, but if you don't grow fast enough relative to this scale, then the hot and cold particles from these two regions mix together faster than the mode will grow, and you would get damping. So if I just balance these two, then I'll get a criterion for R over L, which is a common parameter. The curvature of the magnetic field is R, and L is the scale length of the density or temperature gradient. And that has to be big enough in order to drive instabilities. Okay. So now I'm going to, with that background, we're going to look at a picture of negative magnetic shear and how that's stabilizing. So this is a cutaway view of now a large aspect ratio tokamak that would go around like that. And we're going to imagine that there is a Rayleigh-Taylor finger over here, that's eddy, that's trying to convect hot plasma from the center out to the edge and cold plasma from the edge out to the core. And if there was no shear in the magnetic field, so magnetic fields were always parallel to each other, then, as we said, these eddies have a short scale perpendicular field, but particles are moving very quickly along the field line. So whatever particles created this eddy, they'll tend to be uniformly distributed along the field line, so that eddy will also appear over here, but because of the twist in the magnetic field, this eddy will now be pointing vertical. Now, standard tokamaks, because they carry more current in the center than in the edge, they have what's called positive shear, normal or positive magnetic shear, in which case the magnetic fields towards the center of the device twist more quickly than the magnetic fields out at the edge. And so an eddy that looks like this will not twist vertical. It will, because of the shear in the magnetic field, it will still point in the direction of the effective gravity. And so this is actually somewhat destabilizing unless you made the shear extremely large and positive. But negative shear can be stabilizing. So with negative magnetic shear, by the time this part of the eddy has gotten to the top, that part of the eddy has gone further, and now this eddy is trying to push plasma up the gravitational effective gravity. And so this here it's stable, and we now have a short region between the unstable. There's a short distance between the unstable region and the stable region, and this can help stabilize the drive of these instabilities. And effects like this might be naturally tapped in stellarators. I'm not going to go into a lot of details right now, but there are improved stellarator designs that are being studied. And one of the possible advantages of stellarators, if you can fix their other problems, is that they have a naturally negative magnetic shear that might contribute to helping improve their performance. Okay. So Frank Yanka, who's here, and Bill Dorland, who's supposed to be here sometime today, back in about 99, 2000, did some gyrokinetic studies of electron temperature gradient-driven turbulence, and found, Bill actually thought this might happen, found that the turbulence was much higher than one expected from scaling from ITG turbulence, if you scale both these to gyrobome units. So this shows the heat conductivity, the heat diffusion coefficient, we call chi instead of, to distinguish it from the particle diffusion coefficient d, but it still has units of step delta x squared over delta t. Let's see, so this is chi versus time. There's a linear instability that grows, it saturates, and then we're in a statistical steady state. This is what they get for ETG, and this is what they got for ITG. Normally, if both these results were normalized to gyrobome, we initially assumed that these would be comparable in gyrobome units. But gyrobome units basically have a gyro radius step size, and the step time is the typical growth rate or eddy turnover time, which would be L over V thermal. That would be the growth time, so the growth rate is V thermal over L. And you plug this in, you find this is CT over EB times rho over L. So that's the Bohm factor, CT over EB. But it's reduced from that by a factor of the gyro radius to gradient scale length that's driving the turbulence. And because the gyro radius for electrons is 60 times smaller than electrons, people had thought that ETG turbulence would be negligible. But because they're finding here that there's some coefficient in front here that for some reason is much larger for ETG than ITG. Right. So it's not right. It's at identical parameters, this would still be, say, 3 times less. Chi E would be 3 times less than chi I. However, often ITG turbulence is very close to marginal, and ETG is further away, and so there are ways to get ETG much stronger. But if the multiplier here had been down here, this bought us a factor of 10 enhancement that was necessary to make it significant. Uh-huh.
Why is the factor 6
What?
deuterium?
This is so I'm comparing deuterium and electrons. So the ratio of the gyro radius for electrons versus the gyro radius for deuterium is about 60.
60.
60. No, sorry. Yeah, 60. Yeah. Now, the reason ETG turbulence is more important is because of it forms these elongated streamers. ITG turbulence tends to be more isotropic, like some of the movies shown yesterday. And the reason ETG has these streamers is because of the difference in the adiabatic species response. For ion temperature gradient turbulence, the electrons are assumed adiabatic because the electrons move very quickly along the field line. Parallel variations along the field line, the transit frequency for electrons along the field line are fast compared to the frequency of the modes. While for ETG turbulence, the adiabatic ion response arises from the perpendicular dynamics of the ions. We have these very fine scale fluctuations, and the ions average over them and give an adiabatic response from their radial motion. So these zonal flows that I said play an important role in the saturation of turbulence. These zonal flows are in this direction. They correspond to a radioelectric field. Ions can, the perpendicular ion dynamics can shield a radioelectric field, while for ITG turbulence, the electrons are constrained to move along the field line, and they cannot shield out a radioelectric field. So the zonal flows are much stronger for ITG and suppress the turbulence. Okay. So now we're going to move to some of the measurements. So this is looking down on top of the NSTX device at Princeton. And in part because of these predictions by Yanko and Dorlin, there was a campaign to try to measure these ultra fine scale fluctuations. These are much higher, because of the electron gyrorated scale, they were very difficult to measure, and diagnostics had not been designed before to look for those. So there was a microwave scattering diagnostic built. There are also other ETGs related measurements that you heard about yesterday on D3D. I'll be talking about the ones here, at Princeton. So they shine in a microwave beam. There's some scattering, and they have an antenna over here. And looking at different angles, they can measure different wave numbers. I won't go through the details. But we're going to compare the measurements. So this is the spectrum of fluctuations, a color bar showing the intensity versus frequency at various times in a discharge. And this shows the temperature profile at an early time and the temperature profile at a late time. At the early time, these were both with I'm pretty sure that the heating was the same in both cases. But the Q profile was reversed. At this time, there was negative magnetic shear. I'm sorry, no. This is not the negative magnetic shear case. I'm going to show you the negative magnetic shear later. So this is just showing you with strong heating that, that produces more of a temperature gradient, and a case where I think we've reduced the heating so there is less temperature gradient.
This is heating, the heating is happening in the core.
Yes, the heating is happening in the core. Yeah.
And it's beam.
Some combination of beams and RF. I don't remember exactly for this shot. Right, so at this time, there's a steeper gradient. And so this is the measured temperature gradient versus time. Normalized, it's grad T over T parameter. And this is the critical gradient from GS2. And it shows that this time, this is steep enough to drive these ETG modes. And at a later time, the temperature gradient is down here, while the critical gradient was up here. And so at this time, we think it should be stable. And in fact, the fluctuations that were observed here have largely gone away. And this is in Matsukato's PRL from a couple years ago. Now, there's a different class of discharges on NSTX where they've made internal transport barriers, and they did that by playing around with the Q profile. Q is essentially the pitch in the magnetic field, and how does that pitch vary as you move from the center of the machine to the edge. So here are things like the density profile, the TE profile, the TI profile, and you see that TE has a region of extremely sharp gradients. So that's where a transport barrier has formed and suppressed the turbulence. And in this case, we believe this is caused by the negative magnetic shear. So it's in this region where Q has the reverse sign as normal. S gets down to -1.5, and it's in the vicinity of that where we get this transport barrier. There are also ion transport barriers in the ion channel. Those tend to be more closely correlated with shear in the toroidal rotation. So we think that if this is a suppression of ITG turbulence, that may be a combination of negative magnetic shear and shear flow. That might not be an accident, because once you suppress the turbulence in this region, you can get this turbulence is both causing ion heat transport and ion momentum transport. So once you start to suppress the turbulence here, you can support a sharper gradient in the flow. But the electrons are not affected much by the flow. They occur much faster than the shearing rate due to these E cross B flows. So this transport barrier, we think, is due just to the negative shear. Howard Hughes' paper contains a lot of scans of different parameters, and they found that the location of these ITBs is not correlated with either Q min or a rational Q surface. But the electron transport barrier in these sets of discharges is correlated with the location of the maximum negative magnetic shear, while the ion transport barrier is more closely correlated with the location of the shear flow, region of extremely large shear flow, although this and that are somewhat correlated.
But the shear flow decides on its own where to have a big,
Well, it's not completely independent of this, because this negative shear stabilizes both ETG and ITG. Once you start to stabilize ITG, you might be stabilizing the momentum transport, so you can more easily drive this gradient. And these are the high K microwave scattering measurements with the transport barrier, where we get a steep gradient, and without the transport barrier. Now, this is going to be somewhat counterintuitive from the Matsukato picture, where the region of strong gradient gave you enough temperature gradient to drive ETG, while this was stable. In this case, both of these are technically above the threshold to drive ETG instabilities. But the Q profile is very different. In the top case, the Q profile is very reversed, strongly negative shear, and here the shear is much weaker. There's a slight reversal, but it's much weaker. And if we look at the measurements at these two times, this blue trace is from this plasma at that time, and this red trace is from this plasma at that time. And we see that with strong negative shear, we get a suppression of electron scale turbulence. So these are in the megahertz range. Fluctuations at K perp rho e of order 0.2, we see a significant 10 dB reduction in the turbulence level there. Now, it's interesting that, I'll come back to this. It's interesting that these were still above the linear threshold to go unstable. And this is actually consistent with Yenko and Dorland's results. Their nonlinear simulations show that negative magnetic shear can reduce the nonlinear transport level by ETG. So it both increases the threshold gradient to drive the instability. So this is plotting the chi-e, the diffusivity, turbulent diffusivity, versus the gradient of the temperature relative to the critical gradient. So negative magnetic shear will increase somewhat the critical gradient to drive the instability. But even if you have enough gradient to be above that, if you have negative shear, the transport does not increase very quickly above the threshold. Well, if you have positive shear, you get much higher increases in turbulence level once you exceed marginal stability. And they actually understood, had a model for why that happens. It wasn't just a blind numerical simulation. I don't know why. Let me come back to this. These dotted lines, so the solid lines are from the nonlinear simulations. These dotted lines are theoretical predictions of the turbulent flux based on a model in which you balance the primary instability growth rate of the ETG mode, or ITG mode. This has been done for ITG as well. You balance that primary instability growth rate with the secondary instability growth rate. The secondary instability growth rate is either fed off of the perpendicular flow gradient, so it's a kind of a Kelvin-Helmholtz drive due to the perpendicular flow gradients, or due to the parallel flow gradients. If K parallel is 0, then you don't drive any V parallel prime, and you just have perpendicular gradients, and you would get a large drive of zonal flows as your secondary instability. I'm sorry, right. And balancing the primary instability growth rate with the zonal flow growth rate would give you turbulence levels up here. If, however, you're able to drive the secondary instability, if it has a high enough K parallel to give you significant parallel flow, this instability is much more easy to excite, and it will more easily suppress or it's easier to balance the primary instability at a lower level. Steve Cowley and Barrett Rogers had studied these two regimes. And this is kind of what's observed in the experiments as well. That here's a plot of chi-e versus the temperature gradient scale length in the experiment. There are a lot of plasmas in normal shears around 0 or positive shears, in which they put up to 6 megawatts of fusion power, and they're not able to get increase the temperature gradient much above this threshold. And the chi-e's they get are quite large. But by operating with negative magnetic shear, moderately negative or more negative, then with just 2 megawatts or 3 megawatts, less power than this case, they can get to much higher temperature gradients. And since the heat flux is essentially the ratio of power divided by the gradient, we have a much lower turbulence level here. That's what allowed us, we needed this lower turbulence level in order to get to a higher gradient.
Presumably, the shot with discharges with lower power and higher temperature and much lower density.
Yes, they could be lower density and
Megawatts and the lower temperature, surely the stored energy is probably higher than in this discharge.
right. So you have so this has half the beam power, so it might have half the density. But the gradient in this case is 6 times bigger, so the stored energy might have only gone up by factor 3, not the full factor 6. You're right. I don't know how much they might have tried to control that by gas puffing. Okay. So we're beginning to try to do direct nonlinear simulations using the gyro code for these types of discharges. This is just a pretty picture to show you simulation. We're doing an annulus from a minor radius of about 0.26 to about the half radius. There are buffer regions near the edge that you can ignore. But this shows the radially extended streamers that one expects in order for ETG to be important. These are quite challenging computationally. Let's see, this shows the spectrum in essentially polyidal wave number and radial wave number. The instabilities, because these are, the primary drive instability essentially has Kr equal to 0, but nonlinearities will spread that out some, and they have to have a finite K theta rho e to drive the instability. But nonlinearly, this is the type of spectrum we get. And that scattering is very important because the microwave diagnostic is measuring wave numbers over here. They're high K, but not quite at the optimal position. But still, it's in the vicinity of the peak drive, and our goal is to eventually do detailed comparisons using synthetic diagnostics to try to do more detailed comparisons with the microwave scattering. Uh-huh.
So the maximum instability for zonal scales?
There are zonal modes at all scales.
So this maximum doesn't indicate where the linear instability?
Yeah. So the linear instability of the ETG mode is maximum about here. You can then look at the zonal flows that are kind of secondary instabilities of that. The zonal flows would be along this axis, and there's a range of possible places.
Are these simulations with adiabatic ion?
No, that's what made them hard. Now, having done that, we're not sure it was essential for this case.
Do you have ITGs in there too?
We resolved down to K theta rho I of about 0.5. So we have non-adiabatic ions, but we don't fully resolve the ion scale, the ITG modes. And it's not, for this range of parameters, and for actually many experimentally relevant range of parameters, I think that there is a recent paper by Gerler and Yanko that show that there are ways, there are cases in which ETG and ITG might be more separable, and they can be simulated independently. Okay, so this shows the heat flux versus radius as measured in the experiment, or as we infer calculating from the beam injection and RF heating. And this is given those temperature profiles, when we run gyro, this is the heat flux profile that we get. So this is essentially an ETG simulation that we think can explain about half of the observed transport. We, in addition, have run TGLF, which is a reduced transport model. This is extremely expensive on tens of thousands of processors. This can be run on a workstation. And it also predicts that about half of the total transport can be explained by, let's see, this is just low K modes, trapped electron modes, and this is the additional transport due to ETG. Now, it might look like we have disagreements, and particularly large disagreements out here, but if we run the TGLF model in a predictive mode, where we tell it what the heat power is, and say, what temperature gradient do you predict it results from that, then this is the temperature profile that we get. So it is slightly hotter than the measured temperature profile, but except near the edge, the discrepancy is not very big. And in particular, the gradients in this region are comparable to the gradients measured. Now, interestingly, we're finding a possible bifurcation in the solution, that either the green line is a solution or the red line is also a solution. And it must be jumping from one type of turbulence to another. Well, the fusion guys know about these types of bifurcations, and we're looking into what's going on in this particular case. I did want to say, while I'm here at the Newton Institute, that these types of simulations were only possible by using a variation of the Newton algorithm to stably solve the transport equations. Uh-huh.
Magnetic shear isn't zero at 22.
No. Yeah.
The difference is not due to hot electron modes. The difference is not due to hot electron modes.
This difference?
Between the green and blue.
Trapped electron modes are included in both calculations. So these are TGLF simulations, including trapped electron modes and ETG. And blue is the measurement. Is the measured
if you
temperature
move to the
profile.
previous slide, what is the reason why there is so little electron transport in
Out here? So what we think is that you have to increase the gradient and the temperature out here. And because of the sensitivities, you increase the gradient a little. Some plasmas are very sensitive to gradients and others are not. In negative magnetic shear, things are not sensitive. But here, things are sensitive, and so you change the temperature profile slightly, change the temperature profile from that to that, and the heat flux will rise from this to that.
Greg, could one run and on the next slide, could one run this transport simulation again, maybe forcing the temperatures to be more equal? I guess there's some error bar, but maybe not a factor of 2 out at 1.6.7.
Yeah. Here, my boundary condition was that the temperatures were equal here. I could, move that, or I could adjust it some. And there's clearly is a long history that somewhere near the edge, the types of core turbulence, ETG, ITG, trapped electron modes that we think occurs in the core, somewhere near the edge that is no longer enough. And measurements seem to indicate that there's a different characteristic to edge turbulence that we don't fully understand.
But moving the starting point into 0.7 or 0.65 or something, that might be a good idea.
Yeah, we would still need some increase in either. The heat flux is scaled like t to the 5 halves. So it's both increasing the temperature and increasing the temperature gradient out here that help us get up to this point. Okay.
Graham, are you concluding from the agreement that you've captured within TGyro, TGLF, the relevant fluctuation and stabilities and everything? You say that this is a good agreement. Is this what are you concluding from this?
Yeah, I mean, somewhere from here on in, I would say that we're in the right ballpark. And as you said yesterday, this might be particularly out here. This is probably outside the experimental errors, but it might be good enough for our application. If I was trying to predict the performance of a fusion reaction, to predict temperature profiles this accurately in the core, I'd be very happy.
What did you say happens outside of R over A equals 0.8?
I don't know. I started my simulation here. But typically, the types of core turbulence models that we use to predict the solution in here, those don't give you enough transport in the edge region. And so we think there are other classes of turbulence. Bruce Scott has talked about them, drift alphane, non-linearly driven instabilities that might require more resolution than we're used to. Maybe you need to include interactions with the scrape-off layer. Okay, so I'm going to wrap up. So in summary, I've given you a little tutorial on the bag curvature drive, talked about the predictions of ETG turbulence, their observations on NSTX, and a little bit about the initial simulations. So thank you very much. Where?
So from what you showed, it seemed like there is not actually a wave number spectrum information about anything.
Oh, I just showed one channel. They do have multiple channels for the wave spectrum.
You had this picture of your gyro spectrum,
Right.
and then you had 3 channels. Is that
Right.
Is that all there is? So basically, this spectrum that I can reconstruct.
Does anybody know? Somebody probably knows better than I. How many channels the NSTX system has? 8.
5 to 8. Something
Yeah.
like that.
Yeah. It's about this 3 to 8.
So there is no actual possibility of checking this spectrum, this whole spectrum.
Not right now. There is some discussion of changing the orientation of the microwave system so that it measures more in this direction, but the current alignment is this. Okay.
Right, and it's because remember yesterday George showed a full reconstruction of this kind of thing.
From VES imaging. Yeah.
Right. So they are putting VES on Mars. Is this going to happen? Are we going to see this?
This is electron scale. The one I showed yesterday, of course, was ion scale, but it's the same, sort of the ion to electron
But
analogy.
the lower bit of it you'll be able to reconstruct.
When VES is deployed on NSTX, well, it's started now, it will basically get that full coverage for the ion scale, K per rho I.
So just that with that.
60 times smaller than that scale, yeah. Somewhere in there is where they're measuring.
And with high K we'll stay with 8.
Yeah. I don't want to run too long.
So your TGLF simulation that you showed about half of the mass comes from TMs, maybe. So the TMs have 5 equal species, right?
Yes.
So
for
they're
the-
not totally suppressed, they're just damped to some level.
Right. This plasma is RF. Is heated by RF only, and turns out E-cross B shear is negligible. We tried varying. Yeah, we tried varying the E-cross B shear and it had no effect. Which is unusual. We were not expecting that because STs usually have such large rotation that dominates, but in this case it wasn't important.
And then, do you know if the TGLF simulations predict 2 humps or just a smooth, continuous spectrum in case space?
It's a quasi-linear based model. I wouldn't know how to trust what it said about that.
At the start of your talk, you said that ion transport is completely neoclassical in NSTX. But later you mentioned that you can still get ion ITBs because you suppress ITG turbulence.
I should qualify, it's typically neoclassical in H-mode plasmas, but not all plasmas on NSTX.
Kind of borderline.
Actually, that's sort of a follow-up on this. When you say ion transport is neoclassical, I think, aren't you specifically referring to heat or thermal transport? So my
Right.
understanding is particle and momentum transport are still found to be anomalous.
Right, right.
I think we should move on, and then we'll have more time for discussion.